them, actually all of them, as far as I know, come without proofs of security, and many are broken. Like one of the more famous examples, there was a company that was publishing obfuscated deaths. So this was they give you a software for computing deaths with a key that's somehow hidden inside the program. So you cannot extract the key. So this is sort of a way of converting symmetric cryptography into asymmetric cryptography, like secret key into public key. And it turns out there was a famous attack by Bonnet, Jacob, and Felton on that you can extract information from it. So ad hoc obfuscation, so people propose things. Usually, as soon as someone looks at it carefully, it turns out not to work as expected. A few years ago, there was a very famous paper by Barak and many other co-authors in crypto on impossibility of general-purpose obfuscation. And this is a very strong paper, and it's strong in one sense and weak in another. So it's, as always, it's all in the order of quantifiers. They say that there is no obfuscator that works on all functions by showing that there is a class of functions which cannot be obfuscated. Like, for example, encryption as an example of a function that doesn't seem to be obfuscatable. But this is impossibility of general-purpose obfuscation. I'm not after general-purpose obfuscation here. You know, when I say that I want a database to look like a lookup oracle, you know, I want to obfuscate lookup of data. Okay, I don't want to obfuscate any polynomial time computation. So in that sense, the fact that general-purpose obfuscation is impossible doesn't really tell me anything for the purposes of practical obfuscation, because who knows, maybe the thing that I want to obfuscate is actually efficiently obfuscatable. So in some sense, this impossibility result doesn't really affect anything I'm going to be talking about. It doesn't say that what I'm planning to do is impossible, so, or even that this class of problems is the class of problems that are associated with obfuscated databases is impossible. So it's good to know that it exists. Now, for a very limited class of functions, which I'm hoping to extend in this talk and in this work, we know that they're obfuscatable. There was a paper in Eurocrypt just last year by Ben Lin, Prabhakaran, and Amit Sahai, showing that point functions are obfuscatable. And point functions, think of hashing. Think of Unix password hashes. So that's an example of obfuscating a quality. So somehow you want, like when you give someone a hash of a password, there is no way, you hope that if the hash function is good, there is no way to extract the password from it. And yet, so think of it as a function that evaluates to 1 on only one point where the password is correct, and on every other password it gives 0. Okay? So it seems like hashing provides a good obfuscation of this point function, and in fact it's provable in the random oracle model, or you can prove it, if you don't like the random oracle model, you can prove it if you just have a good hash function. But point functions are obfuscatable, and we use it every day when we type in our passwords. And that's, as far as I know, that's all that's known about provable obfuscation. That's general purpose obfuscation is impossible, point functions are obfuscatable. And databases are somewhere in the middle. So, well, let's see what we can do. So, okay. So the basic approach that I'm going to use in presenting this and defining correctness is based on simulatability and the ideal functionality. And if you are familiar with cryptography, with modern theoretical cryptography, this will be very, very recognizable. And if you haven't had that experience, then maybe it's a little bit obscure. So I'll spend some time trying to give you an intuition for why the definitions look like what they look like. So, but I have to apologize if you're familiar with work on secure multi-party computation, these definitions are going to look completely standard to you, so there will be no surprises here. So it starts by defining what's called ideal functionality for obfuscated database. This is what we want our database to look like. So I said we want our database to behave like a lookup function. So this means that the ideal functionality is the lookup function. And the ideal functionality, it's secure by definition, okay? Because it describes only legitimate queries and or access patterns. Like if I say it's a lookup function, that's immediately clear. Like if the only thing you have as a lookup function from names to phones, then there is no way to evaluate this lookup function so that it gives you a name in response to a phone. Its argument is a name, and it returns a phone. Okay? So this is the ideal functionality. That's what I want my thing to look like. And now I'm saying that obfuscation is good, or it's a real obfuscation, once I define the obfuscation algorithm, is if there is no efficient algorithm, that is, no efficient adversary, can tell the difference between the obfuscated database and something that's simulated in the ideal functionality. So what I'm after, I want to argue that my obfuscation algorithm is good if the result of this algorithm does not leak any information beyond what's given by the ideal functionality. So it's kind of like a two-step reasoning. The ideal functionality I define is secure by design, okay? So, and if the real obfuscation does not leak any more information than the ideal functionality, this means that the obfuscation is good, that no more information can be extracted from it than permitted by ideal functionality. And as I mentioned, this is a standard notion in secure multi-party computation. Of course, here there is no multi-party computation. I'm just giving you the data. But the definitions are exactly the same in some sense. Okay? So any questions about this? So this kind of really high-level idea of defining what you want your thing to look like and then arguing that it leaks no more information. I think I have a picture even here, like trying to explain this intuition. So on the left here, blue, we have the original database, which is obfuscated. And on the right, we have ideal functionality, which is secure by definition. And the claim is that if there is a simulator, if there is an efficient algorithm that produces a fake obfuscated database, so this fake obfuscated database is secure by definition. And the reason it's secure by definition is because it is created without access to the original database. It's only created with access to the ideal functionality. So the simulator who creates it does not know what is in the original database. All the simulator knows is what's permitted by the ideal functionality, so that's secure by definition. That cannot leak any information because it's not even based on the real database, okay? And now the claim is that if no efficient, that is no probabilistic polynomial time adversary, can tell the difference between a fake obfuscation, which doesn't leak anything by definition, and the real obfuscation. This means that the real obfuscation based on the real database does not contain any more information than the ideal functionality. And so for the first example, I'm just going to use it to show, just for a simple lookup function, how this can be done, how you can scramble the database so that it's not all that different from a lookup function. Okay, and as always, it has to be, they can tell the difference with more than negligible probability. So this is computational security, not information theoretic security. We're just saying that it's computationally infeasible to tell the difference. Okay, so now going from this, so this is the formal definition, and I'm giving it for a lookup function. So let me try to go through it so that it doesn't look so scary. So we have a database, and let's just, for the purposes of this talk, I can do it in a more general setting, but for the purposes of this talk, the database is a list of pairs x and y. Okay? But the ideal functionality is a function which, given x, returns the list of all y's such that there is a row in the database where this y appears next to x. Okay? I hope you see the difference. Like if I have just a list of x and y's, I can just look at y's without supplying any x. But the only way to extract y from ideal functionality is to supply x. And if I don't know x, then there is no way for me to extract any y's from the ideal functionality. So it's clear that ideal functionality, the lookup function in this case, leaks much less information than the original database. And in particular, it determines how you can access it. That is the only way to get y's, to supply the corresponding x. And then I say that an obfuscation, that something is an obfuscation of the database if it satisfies three properties. Okay, there are only two on this slide. I'll tell you the third a little bit later. So the first one is probably correct retrieval. That is, with overwhelming probability, if you give it x, what it returns is exactly the same as a lookup function would